Going on now to Chapter 2, Section 1. The title of it is Functions, but there's also three other key terms here that I want to review with you as a sort of an introduction. Relation. Well, some of the things we didn't cover as a review in Chapter 1, but if you don't know about them, you should go back and look at Lesson 1.5 in Math 100, which is UB Math Zone. Look for the lessons on Section 1.5. And you need to know this, that when we are doing graphing, and this is the x-axis and this is the y-axis, we have ways of plotting on this axis the graph, the rectangular coordinate plane here, using an x value which is along the x-axis and a y value which is along the y-axis. If the ordered pair was, let's say, 2, 3, then you would go over 2 and you would go up 3, and this would be the point, 2, 3. So this is considered what is called an ordered pair, and this is an example of an ordered pair. It must be in this order. The x comes first and then the y, and you can plot it. So would you consider these numbers 2 and 3 to be somehow connected? And you might say, yes, they're an ordered pair. Well, this is an illustration of what a relation is. These are related. Now, within this particular relation, we have the letter x. That is the first element in each of these ordered pairs. Well, that is considered the domain. The x elements are the domain. And the y elements, which is the 3 here, is considered the range. So a way to remember it is domain and range, D and R, alphabetically, matches up with X and Y. So the D is the first, along with the X is the first, range is the second, along with Y, which comes later alphabetically. Now, then we have the word function, which has a special meaning. Now, the meaning of function is that the x element here is only used once in a series of relations. It's too much to write out. So, a little background, and these are what we'll be going over. Now, here they're asking us to determine whether each, you can substitute relation here for the word correspondence, is a function. Now, think of this first column as your x items and the second column as your y items. Now we're saying something is a function if the x item is only used once in a combination. So as you look at this, how many arrows are coming from the x side? Well, 1 for each item. So since the 5 is only used once, the 6 only used once, the 8 only used once, this is yes, this is a function, because the x element is only used once. Now, if I had another line from the 6 here, which I don't have, like so, this would then not be a function because the 6 is used twice. Okay. Now, the correspondence matching the numbers with 8 and each number's cube. So I'll have to set that up. I could have picked this out mentally, but if you're not sure of something, you write it out. So there is 5 and it's cubed, 6 and it's cubed, 7 and it's cubed, 8 and it's cubed. Are the x elements only used once? Yes. So this is a function. All right, now they're asking us for the following relations or correspondence. Write the domain. Later, we're going to write the range. And then we're going to determine whether the relation, the correspondence, is a function. So here we're going to have D equals, and we put them in what we call roster notation, a -3. Now, if something is repeated as it is here, you only write it once, a 0 and a 4, and you separate them by commas. Let me write it out anyway. That would be the domain. And then the range would be a 4, a 5, 4, 5, 9, and 11. Just picking up the y elements. Now, as we look at this, is the x element repeated? Yes, it's repeated right there. Now, in the domain, we only write it once, but we see that it's used twice, so this is not a function. And over here, they want us to do the same thing. So domain 0, 1, 2, 4, and range -6, 0, 3, 10. Now again, our x elements are only used once, so this is a function. Okay? So again, you'll have practice and you'll have quiz-mes on this material. Raise it up a little. Now here they're giving us some graphs, and we are to determine first, well, let me study this a little here. So here they want us to put some values here and then look at this graph and pick out the values. Now the letter I indicates this is like 1. This is like a 1 here. This is like a 2, 3, and this is a 4 here. So they're just using a funny kind of Roman numerals. That was messing me up a little bit, but after looking at it, that's what I think they're asking. So they're saying that f of x, this indicates its x value here. So that's going to be a 3 there. And I guess we're using the same values for the other one too. So that will be a 3 there. And then they're asking us later to determine over here that they're saying y equals 2. Y equals 2. Okay. So they could have made it a lot simpler, but they're giving us this challenge of interpreting what they're writing here. Okay, let's take a look at that. Pieces here. Here, if x is 3, well, we go on our graph, and x is 3 right there. So when x is 3, what will y be? Well, y is going to be a negative 2. So if x is 3, 3, negative 2 is that point right there. Now they're saying y is 2. Well, where is y2? Y is 2 right there. And what is x then? X there is 1. So looking at this graph, we were able to get these 2 points. And now let's take a look at this one. Here x is going to be 3. So it's 1, 2, 3 right there. And this is going to be 1, 2, 3. Y is 3. When x is 3, y is 3. Now how about when y is 2? We go up here. When y is 2, x is 0. All right, did I get everything here? And it wants to know the domain of the graph and the range of the graph. Okay, so let's look at the first one for its domain. Now, domain are x values. So this, in a sense, goes all the way out to negative infinity for its x values. So this is going to be from negative infinity, and this goes out this way here too to positive infinity. So that's our domain. Our x values, and it covers that, is this. Now how about our range? Well, it's coming up from our y values, coming up from negative infinity, goes up, 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 but it stops here. It stops here. And this is 1, 2, 3, 4, 5, 6. It stops at 6. And we indicate that where that 6 is included in the range with a bracket. So again, if you're not sure of this, you'll need to look at a reference from Math 100. But that's the domain and range of this graph. And for this one, now our range, let's do our domain first. Never mind range. Domain first, x. It starts right here. We project it down to this line. So it starts, and it is included a negative 1. And it's going on to positive infinity. Infinity always ends with a parenthesis. Begins with a parenthesis, ends with a parenthesis. Infinity. Now the range we project to this line is starting here at a positive 1, and eventually this goes up to infinity. So for number 2, that's what that is. And we'll pause. Now there's a lot of algebra going on here. As we look at number 3, they're asking us, and this, by the way, is function notation, and we can always replace this with the letter y, and that equals n plus 6. But we are going to substitute a 3 for the n. So I've set up a little t-chart to organize our data. And remember, this value is the x value, in a sense, the n value there. So I could put like an n there instead of you don't want an x, that's fine. So it's 3 though. So 3 plus 6, putting the 3 right there, 3 plus 6 is going to be 9 for that one. And then over here, we're putting x plus 1 there. Here's where it gets a little challenging. N then is x plus 1. X plus 1 is our n, and now we're going to add 6 to it. So this is going to give us x plus 7. And let's see if we can find these down here somewhere. 4a, no, 3. 3a here is 9. X plus 7, good. Glad we're on the same page. Now for letter B, this is a little more challenging. So let me pause. We'll take it item by item. So basically what they want us to do in this function is to put where the letter is a 1. So this A is a 1. 1 minus 3 is negative 2. This A is a 1. So 2 times 1 is 2, plus 1 is 3. So our first answer for this value is a negative 2/3. And now we'll do the next one. We're going to put a 3 there. So this is 3 minus 3 over 2 times 3 is 6 plus 1. We have a 0 over 7. And 0 divided by anything other than 0 is 0. So that's where they get that 0 right there. Okay. We're now going to take a look at C, and we're asked to determine what is the domain of this function. Now, the domain of the function is determined by any value for x, but x cannot make the denominator a 0. You can't have a denominator of 0. That's undefined. So what we need to do here then is determine what values of x would make our denominator a 0. So we simply equate our denominator to 0, and we get the equation 2x minus 8 equals 0. 2x equals 8, x equals 4. So your domain for this particular fraction can be any number, but it cannot be a 4. Because if we put a 4 there, 2 times 4 is 8. 8 minus 8 makes our denominator a 0. So let's take a look how they want us to write this. Okay, they are using what is called roster, or I should say set builder notation. It's a modification of roster. You put it in a bracket and you say x is such that x is a real number, so it's all real numbers, but cannot be 4. Okay? Why? Because 4 would make this denominator a 0. Now, for letter D, they want us to look at this absolute value of something and see what values of x, if any, are excluded. Now, x here can actually be any real number, because no matter what that number is, it's always going to come out positive. So we say then in this case, there are no exclusions. X is all real numbers, our domain. And when we have something like this, are there any exclusions? Again, 1 is in the denominator, but it doesn't make any difference as long as we have any number up here as long as it's not in the denominator and make that denominator a 0, there are no exclusions. So this is all real numbers. And here our denominator is a 9. There is no exclusions here. It's all real numbers. And these are down here as well. But let me give you one other. Suppose you have something like this, and I kind of recall seeing this. Suppose you have the square root of something where it says x minus 3 is our function here. Now, for something like this, we do have exclusions. We can't have any number under the radical sign that is a negative number. So it has to be a positive number, or the results of doing what's under the radical sign becomes a 0 or a positive number. So if you get something like this, this is equal to 0. We go x minus 3 equals 0. X is greater or equal to 3 when we bring this over to the other side. So it has to be a number that is either equal to or greater than 0. Now again, you didn't have this one, but this is something you might have. So what would be your answer here? Well, x, let's put x there, and we'll put it in set builder notation. X is such that x is greater or equal to 3. That would be your answer. Now, what does that mean? Well, if the number is 3, 3 minus 3 is 0. So that's good. You can have a 0 as under the radical sign. But if x were 2, 2 minus 3 would make this a negative 1. And you can't have a negative number under the radical. So if there's a number in the denominator, it cannot make, the x value cannot make that denominator a 0. If it's under the radical sign, you can't have a value of x that would make that radicand a negative number. And you just equate it to 0, equate this to 0, and then you find out your numbers. Again, this is sort of an extra one. They're not asking you that here. Okay, let's look at this last one. And normally, we didn't do this in Math 100. This is Piecewise, and I'm not sure they're going to ask you to do it here. But let me just give you a little brief background on it. Now, in this section, this is considered a piecewise function. So we have a piece of it is this, and a piece of it is that. And we have some qualifiers here, but I've made a little t-chart, and I've put under the x values, which is what this is, a -4 and then a 1. Well, which values is less than or equal to 0? Well, our -4 is. So the -4 applies to this one. So we have then a -4 for our x. -4 plus 4 is going to be 0. And that's that pair right there. And then we have a 1, and it doesn't apply here. It applies here. It's greater than 0, which would be the 1. So 4 times 1 is 4. And these are our two values down there. They're only showing you the y values here. Y is 0, y is 4. And then over here, something similar. And remember, this is g of x here. And this one was f of x. We can always substitute the y. So our values are a -4 and a 1. That's what we want to find out. We put it in this T-chart to help organize. So it says x is less than -4. Well, so it took me a little time to understand what they're asking. But notice here in this function, y equals x squared, do we have any values that meet that criteria that x is less than -4? And the answer is no, because this member now is not included in there. So we don't have any values. In fact, we have x is greater or equal to -4. That one applies there. And the 1 applies to this one also. So we don't have any values that meet this criteria because of this exception here. So both of these values will apply to this equation, y equals 3x squared, where they're using the function of g here. So x is going to be a -4 that we're squaring, gives us a 16, times 3 gives us our 48. And then 1 also applies here. X squared is 1. 3 times 1 is 3, and that's what we get. So these are our answers. I don't think you're going to get some of this on your work. This is sort of advanced, and this is just meant to be a light review. Okay, but let's continue, and we'll be working on our next one here shortly.